Okay, I have another test set up to look at a collision. It's going to be in some ways similar to what we did with the two buggies, only instead of colliding two buggies, there's going to be a collision between a cart and a wall. And the collision is going to happen with a spring to let it bounce back elastically. And connected to the buggy and the spring is a force sensor. So I can measure the force acting on this cart that makes it kind of bounce back. At the same time, I also have a motion sensor. So this motion sensor will tell me what the speed of the cart is before and after the collision. So I can collect a bunch of data. So as I get ready to do this, actually I guess we're ready. So my sensor's ready. I have my software ready. Like remember my passcode. Okay, so there we go. There's the sensors. Press collect. Here we go. Oh, wait. Before we do that, I should make you make a prediction. I'd like you to predict what you think the force versus time graph will look like for this force sensor. So as the force sensor comes along, hits the wall and bounces back, what will the force versus time graph look like? Okay, I think we're ready. Once again, cart, force sensor, phone with all the goodies. It's going to record all the data. I'm going to press collect, and hopefully we get some nice graphs here. There we go. There's the force versus time graph. Is that what you were expecting to see? Here's something that might be useful or interesting to add to our experiment. So I have a balance here, and it's measuring grams, and I have the cart and force sensor that we're using. So let's find out its mass. Down there, like that. So mass of 375.7 grams, or 0.3757 kilograms. So here's the data from the lab. So I have a force versus time graph and a position time graph. So from this thing, we can see that the peak force was at 2.5 seconds. It looked like it went up to 4 newtons. There's one thing we could analyze here, and that would be the area under this curve. So I'm going to pick that curve, and then I'm going to choose, it's called integral, but it's going to calculate the area. And that gives me 0.505 Newton seconds. So the units would be like, it's an area, so it's like this times, it's like the force times the time, which is Newton times second, Newton second. So let's write that down. Force times time equals 0.505 Newton seconds. This is the area under the force time graph. And I think that's about the only useful thing we can get off of this graph, the peak force and then the area. Like the slope, I don't think, I'm not so sure that matters so much. This graph, we know it started, I guess, just depending where the motion sensor was, it started 2.43, then moved up forwards and backwards. So I think one thing that might be interesting on this, if we find the slope of a position time graph, we get velocity. So why don't we do that? Let's find out what the slope of this line is. If we get the slope of this line, we'll know the speed that it was going before it hit, and then we could also get the speed after it hit. So I'm going to use the curve fit, I think it is, yeah, curve fit. And it's linear, so I'm going to go OK. And y equals mx plus b, it tells me the slope is 0.7015. So that's the speed going into before the collision. Or velocity before collision. what was it again? 0.77015 meters per second. All right, now let's find what the, get rid of that. Let's find out what the velocity is after the collision. So let's pick that area, apply curve fit. Yes, it's linear. And the slope of this is negative 0.6577. Okay. And what did I say the mass of the cart was? I think I said the mass was mass equals 375.7 grams or 0.3757 kilograms. Well, what's something we could change? We could calculate. We could calculate the momentum before. So that's equal to 0.3757 times 0.7015. Okay, so that's kilograms meters per second. And momentum after equals 0.3757 times negative 0.6577. So that's that kilograms per meter second. So that's kind of interesting. Oops. Actually, when I look at these two numbers, they're pretty close. They're not quite. I wonder what happens when you add those two, when you find the difference. What happens if we go change in momentum? So dp, delta p. Delta p. Oops. Maybe I'll just use the equation editor. There we go. Delta p equals P final minus P initial. Okay, so that's equal to, so that's negative 0.2471 minus 0.2636. That is it. Well, will you look at that? That and that look to be really similar. Perhaps that's a new model that we have. Is the force times time equal to the change in momentum? Let's take a look using equations. Force times time. This is the question. Is that true? Well, let's do this then. Force times delta t. Delta p is equal to m delta v, because the mass stayed the same. It was the velocity that was changing. Okay, now let's divide both sides by delta t. That cancels out. And will you look at that? What's delta v over delta t? What's that equal to? I believe that is F equals ma. That's Newton's second law. And I think if we believe this is true, and we believe the algebra is correct, and this looks like, this looks like it's pretty solid data to support it, I think we have a new model. And I think that's this one. And we'll even give that a name. F times delta t is equal to impulse. And we're going to use that in our momentum unit as well.